from ICMAT in Madrid, and today's talk's title is Quadratic Normality and Triple Curve of Threefold in P5.
Okay, so thank you again. So today we'll speak about two-normality, quadratic normality, and triple curves of threefolds in P5. This is joint work. This is joint work with Emilia Mezzetti and Pietro De Poi. And Mezzetti. So let me start by explaining why I'm interested in this particular problem of the triple curve of a threefold in P5. So let me give some motivation to the problem. So in this talk I will denote by X in Pn will be a smooth, irreducible, complex manifold of dimension n. N will be the dimension, and C will denote the codimension. Again, X is non-degenerate. So this number is nothing but n minus n. And the motivation of this is comes from famous conjecture, Hausers conjecture, saying that if n is greater than or equal to 2c plus 1, then X is a complete intersection, meaning that the ideal of X is generated by exactly C homogeneous polynomials. Okay, this is maybe the most famous conjecture in projective geometry, and let me remark that if X is a smooth, I said that X is smooth, so I won't write smooth again. If X is a complete intersection, then X is projectively normal. Meaning that the coordinate ring is an integrally closed domain, but maybe it's better to define projectively normal in the more usual way, saying that these maps, natural maps from global sections of Pn, K onto the global section of O, X. This is a surjection for every K. Or if you prefer, this is equivalent to say that H1 of the ideal K is 0. So this is the definition of K normality, right? Right? It's K normal if one of these two holds, and it's projectively normal when it holds for every K. Okay, so the remark is that one can study K normality as an intermediate step towards Hausers conjecture. Okay, so the first step is to understand the case K equal to 1 One normality is usually called linear normality, and in this case most of the things are due to Fyodor-Zak, solved by Zak in two famous results. The first one, theorem, is the so-called Zak's theorem on linear normality. This theorem says that if n is greater than 2c minus 1, then x is linearly normal, or one normal if you prefer. Second theorem is the classification of the cases on the boundary. So this is Zak's classification of subvarieties. Namely, if n is equal to 2c minus 2 and x is not linearly normal, then x is a subvariety. You know that there are 4 of these: the Baroness embedding of P2, P2 cross P2, the Grassmannian of lines in P5, and the Cartan variety that we saw yesterday. And to complete the picture, let me remind, as a simple remark, so the conjecture is for 2c plus 1. Here we have 2c minus 1, 2c minus 2. So in the remaining case, if n is equal to 2c, there are some examples which are not complete intersections. There exist some examples not complete intersection. For instance, the Grassmannian of lines in P4 embedded naturally in P9 with the Plucker embedding, and the Spinor variety S4. This is a variety of dimension 10 inside P15. Okay. These are not the only ones, but these are the examples that motivated mainly Hausers' conjecture. Okay, so the picture is more or less clear for k equal to 1. But if we consider k, Grassmannian of lines in P4. P15, right. This is the variety of 4-dimensional linear subspace inside the quadric of dimension 8, inside P9. If you want a projective description, there are intrinsic description with representation coming from representation theory, but so this is more or less the picture for k equal to 1 for linear normality. For quadratic normality, this is almost open. I mean, it's open. There are no results so complete like this. So maybe it's better to start with the first case. So we start with the case c equal to 2. Right? Okay, so if c is equal to 2, then Hausers' conjecture predicts a complete intersection for n greater than or equal to, so this is n to c, so n equal to 5, or if you prefer, n greater than or equal to 7. But let me point out that if you have if you have a subvariety, if X in Pn is subcanonical, meaning the canonical bundle is like this, and then it's greater than or equal to 3, then there exists a vector bundle E over Pn of rank 2, and there exists a section such that X is given as by the degeneracy locus of this section, so such that we have this picture, this diagram, exact sequence. We have OPN. This is multiplication by S. This is E. And here we have the ideal sheaf of X. Okay. And this is Hausers search corresponder, right? This is Hausers search correspondence. And in this setting, we have that the vector bundle splits, namely is isomorphic to O alpha plus O beta over Pn. If and only if X is a complete intersection. Okay. But now remember that there are no examples of indecomposable vector rank 2 vector bundles over P5 or more. So Hausers conjecture for codimension 2 can be written in this way. So conjecture, Hausers conjecture for C equal to 2 can be written in this way. If X in P5 is subcanonical, then X is a complete intersection, and if n is greater than or equal to 6, we get subcanonicity because we have Barton-Larsen theorem, and then one spec X is a complete intersection. Right? Let me recall that for n greater than or equal to 6, the Picard group of X is generated by the hyperplane section by Barton-Larsen theorem. Right. And the motivation of this conjecture, which is slightly stronger than the other one because Hausers conjecture is for n greater than or equal to 7. This is for n greater than or equal to 5 under the assumption of subcanonical, and for n greater than or equal to 6. In general, it's also due to the lack of examples of indecomposable rank 2 vector bundles on projective spaces, right? There are examples in P4, for instance, the Horrocks-Mumford bundle, right, which is not decomposable, but in P5 for higher dimension there are no.
So how about if we does not assume the subcanonicalness?
If you don't have Hausers search correspondence, this is a necessary condition. When X is subcanonical, you have this vector bundle, which is an extension of the normal bundle of the variety. So necessarily.
So we are assuming the subcanonical, then we can put Hausers conjecture equal to the split list of the vector.
Okay. Very good. So let's come back to K-normality. In this setting, C equal to 2, because for K equal to 1, the picture is more or less clear. But for K equal to 2, there are some interesting conjectures that I want to speak about. So let me start. Supposing C equal to 2, the first case could be n equal to 3. But here we have curves in P3, and there are no restriction because every curve can be embedded in P3. So this is not interesting. Next case is n equal to 4. Okay, for n equal to 4, the first thing to consider is one normality, linear normality. And in this direction we have Severi's theorem of Severi, saying that if X in P4 is non-linearly normal, then X is the Veronese surface, if you prefer the projected Veronese surface. Okay. So let me explain how can you see this Veronese surface in P4. Consider this vector bundle. This is a globally generated vector bundle, and consider 3 general sections of this. Okay. Then the degeneracy locus of this map gives you a smooth surface here, which is precisely the Veronese surface. So here we have to write the C1 of this is minus 5 plus 2 times 4, so minus 5 plus 8, so this is 3, right? Okay, so this is the Veronese surface. Veronese MP4. Geometrically, we have G14. We have G14 in P9. So consider the intersection of this variety with 3 hyperplanes, because here we're taking 3 sections. We have, let me denote sigma, will be G14 intersected with H1, H2, and H3. And this sigma, this is a linear congruence of order 1. Let me try to explain these words. Linear means that is obtained by intersecting G with hyperplanes. Intersecting G with hyperplanes. Congruence in general means that the dimension of this is half the dimension of the ambient. So the dimension of sigma is 3, the dimension of G is 6. Every time you have something of the dimension, half of the dimension of the Grassmannian of lines, this is classically called a congruence. And of order 1 means that if we consider the standard diagram, the universal incidence variety. So these are lines in P4. Here we have P4, and here we have couples LP such that P belongs to L. Right? Then this order 1 means that this is of dimension 3, the fiber is of dimension 1, so this is something of dimension 4, and order 1 means that this is a birational map. This is what order 1 means. Okay? But now, so what is X here? This is a birational map, so the fundamental locus of this map and the branch locus coincide. Okay, the branch locus is the image of the ramification divisor here, something of dimension 3. But the image of a point here in the branch locus cannot be finite by Zarinsky main theorem. Right? So the fundamental locus, the definition of fundamental locus is the set of points through which passes infinitely many lines, okay, coincide with the focal locus. Okay, so on the other hand, for every line there are three focal points, sorry. This is the general thing in the theory of focal loci. And so what you get is a surface X here, the projected Veronese in P4, such that through the general point there is just one trisecant line. Okay, so these are the three focal points which are actually fundamental in the sense that through these points there are infinitely many trisecant lines. Right? And this is clear for Veronese, because for Veronese, when you project into P4, every plane containing a conic contains also another point. So this point is in X. This is of course in X. So here you have infinitely many trisecant lines. Right? Okay, is clear this construction? So you start with this bundle, which is globally generated. You take three sections.
In this picture, the conic is inside the Veronese surface.
Yeah, this is also containing X.
And the point also
is in X.
is in X.
Yeah.
So they have some trisecant line.
Infinitely many.
But this is in P5?
This is in P4.
P4, yeah.
Yeah. I'm trying to explain how to think of the Veronese surface in P4. I mean, in P5 it's clear, and when you project, you get this picture. Exactly this. You get that the Veronese surface in P4 is the fundamental locus of a linear congruence of order 1. I mean, linear congruences are always of order 1. This is simple Schubert calculus in Grassmannian, in the sense that this map is always birational. Okay? So every time you have a linear congruence, this is birational. And in this case, what you get as the fundamental locus is exactly the Veronese surface.
So what is the definition of fundamental locus?
Fundamental locus is the set of points here such that the fiber is of positive dimension. And when this is something of birational, this coincides with the branch locus of this map. Okay? Because by Zarinsky main theorem, fibers are connected, so cannot be finite, so must be a positive dimension, right? And I have explained in detail this example because the Palatini scroll can also be described in the same way. So let me start first as a consequence, so corollary. I will denote this star. You will see in a minute why. So as a corollary, if x in P4 is not one normal, then the double curve is reducible. So what's a double curve? So here we have Veronese in P4. If I take a general point, there is just a trisecant line. Okay. But for any 2 points in the Veronese surface, there is a conic. So there is a conic here, there is a conic here, and there is a conic here. Okay? So when I project from this point into P3, I have this triple point corresponds to this picture. This is the double curve. Right? I mean, you can think of the double curve downstairs or upstairs. It's the same. It doesn't. You think downstairs it's the union of 3 lines. If you think of this double curve upstairs, it's the union of 3 conics. Doesn't matter, right? And this point corresponds to the triple point coming from the unique trisecant line passing through the general point. Right? So in this case, this is 3 conics. Okay. But this implication is a posteriori. In the sense, after we have Severi's theorem, if x is not too normal, then it's a Veronese surface, then I compute it and I get 3 conics, reducible double locus. I will see later how to prove this statement a priori. I mean, without Severi's theorem. Assume that this is not one normal, and we will see that the double curve is reducible. Okay? But first, let me introduce a Palatini threefold. So a posteriori means after Severi.
So what do you mean 3 conics? 3 conics. This is in the image. This is just 3 lines.
I mean, if you prefer, you can define the double locus upstairs or downstairs. It's the same. 3 lines. This is in P4. This is in P3. This is not a problem. So let's consider a similar construction, but now in P5. So I take the cotangent bundle in P5, twisted by 2. This is globally generated. I take 4 sections of this. P5. Okay. This map is generically injective, and the generacy locus of this map between bundles gives me the ideal of a threefold. In this case, the C1 is minus 6 plus 10, so this is 4. Okay. And this variety here is the Palatini threefold. Palatini scrolled. because it has a structure of scroll in the sense that it's a two-dimensional family of lines, of disjoint lines in P5, and the base is a cubic surface. Okay, but I prefer this description because with this description you can see easily what is H1 of 2. Well, this is -2, this is omega, this is J2, so this is exactly 1, right? The same way here you see that H1 is 1, so this is not 1 normal, so this is not 2 normal. Okay, this is the right way, in my opinion, to present the Palatini threefold, and geometrically one has the same construction. Now we are in P5, so we have the Grassmannian of lines in P5. This is variety in P14, and I consider sigma, the intersection of G. Now with 4 hyperplanes, H1, H2, H3, and H4. So this is something of dimension 8, this is something of dimension 4. And once again, this is sigma, is a linear congruence of order 1. Now you understand what I mean when I say linear congruences of order 1. Here the picture is slightly different because when you fix a line, there are 4 focal points. So now in this case you have in P5, these are the focal points or fundamental points. I mean, X is the fundamental scheme of this congruence. X is the fundamental scheme of the congruence sigma. So we are in P5, we have this threefold. And now what we get is that through the general point there is just 1 because this is of order 1. But this is a 4-secant line. Okay? Well, and moreover, if we consider the triple curve, so now I have P5, I consider general point here. Here we have X. I project onto P4. Okay, through this point there is a 4-secant line. And one can see that there is, every time I fix 3 of these points, there is a plane cubic passing through them. Okay, so if I fix these 3, here there is a plane, and here I have a plane cubic. And they have the same if I change this point. Okay, so I have 4 plane cubics, and actually what I get is something like this here. So these are 4 lines, these are triple points, and this is the unique quadruple point. Okay, and here I have so the triple locus is the union of 4 cubic, plane cubic. in particular, it is reducible. Okay.
So can you describe the defined equation more precisely?
What the equations?
It is defined by dependent locus of the defect bundles, but so can you precisely give some equations of cubics?
Well, no, I can't. I should think a bit. I mean,
So how many cubics really?
you want to know how many cubics contain the Palatini threefold?
Yeah.
No, there are no cubics because
Quartic.
yeah, there are quartics.
Yeah, so we can count it by just using the random sequences. But,
I think so, because you have this, no?
yeah, you're right.
Once you have this description, you can compute the number.
Yeah, sure. But it can be concretely described or not?
I think so. I think so. I think it should be two quartics, right?
Two quartics, maybe, yeah.
Maybe we can try later to compute it, but should be two. More? There are more?
Because that's the particle distance for regular. Maybe.
So let's see.
Yeah, so
You want.
more than that.
So you want the H0 of this. So you just need the. Ah no, you're right. It's bigger. It's a bigger.
Yeah, bigger.
Yeah. Yeah, of course, because H0 here is 15.
Really?
Right? Yeah, because this is embedded in P. I mean, this P14 corresponds to the global sections here.
Yeah.
And this H0 is 4.
That's yeah, so 11.
So it's a big number. Ah,
11 parts.
okay. So H0. Okay, so I said that in particular this triple locus is reducible. And so you see, this is a similar picture of the Veronese surface. Let me point out that in general one can repeat this construction for higher dimensional projective spaces, but you get singular schemes here, because the degeneracy locus, the codimension of the singular locus is 6, expected to be 6. So as soon as you get P6 or more, then you get singular examples. So let me remark that if n is greater than or equal to 6, then same construction gives singular x. Okay. Good. So coming back to the quadratic normality, here we have an example of threefold which is not too normal, and there was a conjecture due to Peskin and Van de Ven saying that if x in P5, we are always assuming C equal to is not too normal, then X is the Palatini scroll. This is a long-standing conjecture. It was 30 years ago. And it's a difficult problem. So in our collaboration with De Poi and Mezzetti, we obtained something, just a partial step through this conjecture that I will state now, theorem. This is De Poi, Mezzetti, and Sierra, saying that if x is not too normal, then the triple curve of x is reducible. I mean, this is a very partial step towards this conjecture, but let me explain the motivation of this result. So what's the strategy? Consider first the case n equal to 2 or n equal 4. Okay, in this case you have something is not one normal, then by Severi this is the Veronese surface. But there is another result characterizing the Veronese surface in P4, which is due to Franchetta. This is due to Franchetta. And characterize the Veronese surface as the only one with reducible double locus. Okay? But I will show in a minute that this is very simple. I mean, if this is not one normal, the double locus is reducible. This is what I wrote here as a corollary with the star, because a posteriori after Severi's theorem it's true, but I will show it a priori, because this is more or less the idea we had in mind when we proved this theorem. So let me write, well, theorem or proposition. I mean, this is not a theorem, maybe proposition. Theorem star a priori. This was done first by Mezzetti and Portelli, but using the monoidal construction and the Igor Notcore complex. But the proof is really long and a bit, it's a mess. I mean, and we found a very simple proof of this statement, just playing with geometry. So let me show you the proof. So the hypothesis x in P4 is not one normal. What does it mean? It means that there exists x prime inside P5, and there exists a point P, maybe P is not good, maybe Q is better, such that the linear projection from Q, from x prime to x, is an isomorphic, right? This is just a definition of not being linearly normal. Okay? Now let me consider, I want to show that the double curve downstairs, I mean in P4, it's reducible. So let P in P4 be general, a general point. Okay. So then p minus 1 of p, p minus 1 of p, I mean this is in p5, not in x prime. This is just the line pq intersected with the secant variety of x prime is a finite number of points that I will denote by q1, qd, where d is exactly the degree of S x prime. But since this is non-degenerate, because this is non-degenerate, x non-degenerate, then this number is greater than or equal to 2, right? Otherwise, x is contained here. If this is 1, this is a P4, so x prime would be degenerate.
Why the pi q inverse p is the line intersection with the secant variety?
I mean, this is not, no. Maybe it's better. Okay. I started to write another thing. So this line intersected with the secant variety of x prime. Here we are in P5. This is the points. These points are different, right? Because P is general. So these points can be chosen generically. They are different points, right? So now let me show you the proof. Okay, now consider the entry locus of these 2 points. Consider the entry locus of Q, say I. Okay, this is the entry locus. This is in X, the entry locus that I defined yesterday. And the key fact is that these entry locus are different. Okay. So I will explain this in detail. So let me maybe make a picture. So here we have P4. Here we have P5. This is the projection from a point Q. This is X prime. This projects isomorphically onto X, right? This is a general point P in P4. So this line intersects here in the points Q1, Q2, QD, and I consider the entry locus of these points. Okay, so here I have something like this, and I consider the entry locus here, right? And the same for the other points. Okay. And I claim that the entry locus cannot coincide. But this is obvious because assume that, for instance, these 2 entry locus coincide. What does this mean? It means that this point is in this entry locus, so this line is to secant, but this line is also to secant. So when I project from this point, the span of these 2 lines is a plane, and this point is inside the plane, right, because it's in this line. So when I project here, I get, where is P? This is P. So I have a trisecant line here. Okay? And this happens for every point. So then I have that for P, every secant line is trisecant because I have infinitely many trisecant lines. And this is not possible. This contradicts the trisecant lemma. Right? So these two are different by the trisecant lemma. Okay? But of course, these two are different, since the projection from this point is an isomorphism, then is different of this one. Okay. So here I have several entry locus, and hence the double curve is reducible. Is this clear? Okay. So basic projective geometry. No monoidal construction, no Egon-Norcott complex, and so on. Okay.
And it appear in your joint paper?
Yeah, it appears as the motivation of this thing, because the proof of this statement is exactly the translation of this thing. It's a bit more complicated because you have to make a double Veronese embedding, because here the variety is not quadratically normal.
Yes.
But essentially it's the same proof. I mean, it's exactly like this thing. I think we will.
So in your original paper, you use two-variety embedding?
Yeah.
Then it is the same argument of the
Exactly. Technically it's a bit more complicated, but the idea is as simple as this.
So why the secant variety of x prime is not the whole space P5?
Because otherwise the point Q belongs to this, and this is not an isomorphism.
Okay.
So implicitly I didn't wrote it, but this is of dimension 4, because Q is not in this variety. Otherwise you don't have an isomorphism.
How about the defect case, two case possibility?
Sorry, what do you mean?
What I mean is it possible to the dimension of the secant here?
To B3? No, it's not possible. Because then it could be projected into P3. And no surface can be projected into P3, right? So 4 is the only possibility. You have that these lines intersect in a number of points. Points can be chosen, I mean, since you can move the point P, these points can be chosen different, and you have the entry locus corresponding to every point, and these entry locus are distinct. Because otherwise you have that through this point, the general secant line is trisecant, and this is a contradiction, right? This is the whole story, nothing more. Okay, so now let me pass to the threefolds in P5. So the program is try to understand the K-normality in codimension 2, where Hausers conjecture is, it's still open, and the expectation is that in P6 they are complete intersections. So the interesting cases are P4 and P5. In P5 there is this conjecture, but let me introduce some things about multi-secant lines. So let me remark that if we have a threefold in P5, then the secant variety is the whole space. So in particular, the entry locus of a point P, the dimension is 2, right? Because we have the family of secant lines is of dimension 6 plus 1, 7 minus 5, 2. This is for P not in X. Okay. Now let me consider, let me denote in this way. S3 of X. This is by definition the union of lines such that the length of L intersected X is at most 3. So this is the union of trisecant lines to X. This is inside P5. And there are two possibilities. First possibility is that these two objects are different. Then it was proved by Quack, and also can be proved using a theorem of Aure, that in this case X is contained, I mean, if the trisecant lines does not fill up the ambient space, then X is contained in a quadric. H0, X2 is different from 0. On the other hand, if the trisecant variety is the whole P5, then let me denote by gamma P. This is the set of points X in X such that the line Px is a trisecant line. Okay. P is a point out of X. Okay. And it's very simple to prove, I will show as a lemma, that this is actually, if non-empty, it's actually a curve. So if gamma is non-empty, then this is for general P. Okay, the proof is very simple. Of course, the dimension is bounded by 1, right? If it was 2, then this contradicts trisecant lemma. So what happens if the dimension is 0? The dimension of this thing is 0. Then we have, since these fill up the ambient space, and through the general point there is a finite number, then we have a 4-dimensional family of trisecant lines, right? Trisecant lines of X. Okay, but now I will intersect with two hyperplanes. So now let C be the intersection of X with two hyperplanes. And then C has finitely many trisecant lines, because every time I cut with a hyperplane, the dimension drops by 2, right? Because the dimension of the Grassmannian of lines in P4 is the dimension of the Grassmannian of lines in P5 minus 2, and so on. So if this is of dimension 4, I cut, the surface has a dimension 2, the curved section has dimension 0. But in this case, you know that actually there are no trisecant lines at all, and that the curve, then C, is either a rational normal curve in P3, right? That's a twisted cubic, or the complete intersection of two quadrics, right? So this is an elliptic normal curve. Here the degree is 3, here the degree is 4. Okay? And this is a contradiction because in this case X is also well known. It's either a complete intersection of P1 cross P2, so it's contained in a quadric, and we get a contradiction. Okay? Therefore, the dimension of this is 1. And I will, yeah.
Why you cut the hyperplane section?
The dimension drops by 2 because here you have the Grassmannian of lines in P5. This is of dimension 8. And here you have the Grassmannian of lines in P4. This is of dimension 6. And here you have the Grassmannian of lines in P3 of dimension 4. And here you have the family of trisecant lines, F, which is, I assume it's of dimension 4. So when you intersect this one with a general something of codimension 4, the intersection theory tells you that you have finitely many.